My name is Bobby Segu, and I'm the Global Product Manager for Protection and Control product line, including the microgrid control solution at GE. It is my pleasure to share our vision with you for the microgrid platform. The microgrid solution provides an economic dispatch engine to operate the microgrid system assets, such as generators, loads, and storage devices in the most optimized fashion. GE Microgrid control solution also features advanced protection and control for the microgrid system assets, including energy devices, controllable loads, renewable energy assets, etc. This short video will give you an overview of many of the capabilities this solution has to offer. Thank you for watching and good luck with your studies.
Hi, this is Hassan Al-Tawil. I've been with GE for about 20 years. I would like to thank Bobby Sagu for his support to the microgrid program. The microgrid topic is very controversial, and our goal is to give you the microgrid from a GE solution perspective. Okay, so we will start to cover a brief history about how did we reach to the point where microgrid age started and it became a common thing that's implemented in many places, and how did we reach to standardization on the microgrid. Next we'll talk about the power grid today and where does microgrid fit in the power grid, just to give you a feeling of what is a microgrid and why we need the microgrid implementation even though we have the bigger grid implemented. We'll talk about the microgrid control and what does it mean to have full control versus just a controller that's controlling the microgrid. We'll close off with one of our many GE solutions that was implemented, basically a microgrid project. Okay, so let's start with a brief history on the microgrid. Over the years, the demand for electricity was increasing. Meanwhile, the resources available to serve this demand were not growing at the same level. As such, there was a requirement for microgrid to be a key component of the entire grid. Okay, so on June 25th, 1998, reliability was an issue for the IEEE, which stands for the Institute of Electrical and Electronics Engineer Standards Board. So the IEEE expanded the Standard Coordinating Committee 21 responsibility to include all distributed generation and energy storages. So in 1998 was the first meeting of the SCC 21. The U.S. Congress declaration to the U.S. Department of Energy in the late 1990s was to explore methods, tools, and technologies to protect and enhance the reliability of the grid. In March 1999, the IEEE approved the initiation of the Standards Development Project P1547, titled IEEE Standard for Interconnecting Distributed Resources with Electrical Power Systems. In 1999, the Consortium for Electric Reliability Solutions was formed to propose solutions for the electrical grid reliabilities, and the main drivers were to reduce the carbon footprint and bring out a standardization for the microgrid to be developed and connect to the main grid. So around the year 2000, we started to see methodologies and tools for connecting and creating microgrids that will be part of the full grid. Around the year 1999-2000, the Consortium for Electric Reliability Technology Solution invited experts from around the world in order to create the microgrid standards. So the aim was to improve and increase the distributed generations, and publications started to show up around the year 2000 to support the requirement. Many utilities started the testing in the year 2006 to 2007. American Electrical Power, AEP, started running lots of tests on the publications and the microgrid standard implementation. Now that we have a brief understanding of the history of microgrid, I'm going to talk to a little bit about the grid today and how the microgrid fits into today's grid. An infinite bus is the goal, is the idea that you have this medium or this grid that you can add as much load as you want to it, and you can add as many generation points to it, and the voltage will not change and the frequency will not change. Everything will stay the same. So the idea of an infinite bus really is an academic approach in order to understand that if everything is kept constant, right, what is required to operate efficiently, right? And because that 100% everything is controlled in an infinite bus does not exist, the voltage is allowed to vary a little and the frequency is allowed to vary a little, and there is modes for the generators in order to accommodate the variation. So you will find that there isn't one generation point in the entire grid that is setting the voltage and the frequency, what's known as isochronous. Instead, all the generators in the microgrid are basically adjusting to the variation and the changes in the microgrid as load is added and as generation points are added to the grid. Nevertheless, the idea of the infinite bus is a perfect idea, and it is the goal of any grid managing utility. Okay, so now that we have a good idea of where does the microgrid fit in a bigger grid, let's discuss about what is a microgrid from a GE perspective. A microgrid is where local electrical energy is generated or stored by small grid devices referred to as distributed energy resources, DER. The system could be set up with or without control capability. According to this concept, there is no master-slave or centralized control scheme. All the resources are connected in a peer-to-peer and plug-and-play fashion with a localized control scheme. A microgrid can either be connected to the grid with all of its distributed energy resources, or in an island without the means of connecting to the grid. A switch can separate the microgrid from the main grid automatically or manually, and it then functions as an island if it is separated. Okay, so like I mentioned, any distributed generation resource can be plug and play and connected to the grid, whether via an inverter, a switch, whatever the means is. So what is the concern to the utility? If that microgrid is managed properly, if it maintains the requirements per the standards, whether we connect a 1 megawatt distributed generation or 10 megawatt distributed generation, if you increase the distributed generation, utilities have to restudy the system. They have to restudy it for false current changes, short circuit capacity changes. They have to then take these studies and generate certain settings. These settings have to then be used to update their system. All of that, the case study, the settings, the updating of the system, translate into heavy cost for the utility. If we can find that perfect microgrid that will never contribute to a fault current, and they don't have to change their system, that will be an ideal situation. But reality of the matter is, if we define our microgrids to be up to 10 megawatts and above, every addition source will have a cost impact to the utility. There are many things that impact the cost of maintaining the quality in a grid for the utility. So for example, they have to maintain the voltage, like we said, and the frequency, and also the kilowatts, the reactive power, the fault, and at the end of the day, the consumer not only wants the utility to provide the quality in each one and each of these aspects, but also to run efficiently without any downtime, without any penalties, and all of that is contributing to the cost of addition of a microgrid. One of the common questions that I hear in training is, okay, well, the utility has established, they have paid for all of this infrastructure, they are providing efficient power. Why do we need a microgrid? Like, it's a cost to the utility. So what's the drivers for implementing a microgrid in an area where that microgrid could be connected to the grid or disconnected from the grid? So let's answer that question. The drivers or the incentives for a microgrid is that the microgrid traditionally was thought of as something for a remote area and does not exist as part or in an area where the grid has reached. In reality, there is many factors where the utilities started to change the way they think about the microgrids, that it is a helper, it is not a competitor of the utility in any way. And even in most cases, there has been cyber attacks or natural disasters where the microgrid was available to support sensitive loads, like think of an airport or a hospital where local distributed generation is required to start up because there has been a major impact to the main grid where it could be days without the grid being operational in certain sector or certain sections. So that is a good reason to avoid also cyber attacks that might impact the distribution devices. All right, and the standards that were published started to have that phrases and wording where it would say that the utilities not only have to make sure that the microgrid connect at the right stability factors for voltage, frequency, and watts, but instead it started to say that this is a helper for the utility. The utility should encourage the implementation of a microgrid as it is a good enabler for the smart grid. So in order to achieve a smarter grid, we need the implementation of a microgrid along the side of improving the utility grid itself. And finally, in order to maintain the quality control in a grid, to maintain the reliability of power to the end consumers, microgrid is seen as a great advantage that will assist those entities that are in need of constant power. Okay, so now we have a microgrid, and the question is what level of controls are we having in the microgrid? What type of controls? We start with the primary level. A primary controlled grid is a simple generation point that feeds power, and the power is fed with the minimum requirements that meet the standard of the local utility. So it just provides enough power. It kicks in when the utility cannot provide the power to the local entity, and it has no automated control available. A second level of control is when you bring in the automated control, you have a controller in place like the DMC 490, and it communicates to the local DERs and control them and make sure that they are providing not only power when there isn't power from the main grid, but providing economical setups where you might want to discharge your battery when the grid provides the power at a more expensive tariff, and it makes more economical sense to use a local battery storage system. And if you want to advance that further, you will have what we call a tertiary or an advanced control, where you have included in your microgrid what they do in the bigger grid. So you have included the functionality of an energy management system and a distribution management system. We'll try to cover this further in future trainings. So now that we understand that the microgrid is required, it is an important part of our grid, I'm going to discuss briefly the microgrid controls and the impact of these controls, different aspects, different parts that will help our learning in the microgrid sector. Okay, so in a microgrid, we have the stability functions, which include, of course, the voltage and the frequency control. With those two, you want to make sure that you have an efficiency achieved. So in order to achieve the efficiency, you would need to control your kilowatts, kilovars, and when is your microgrid going to utilize the grid, when is it going to utilize only the microgrid. Some of the functionality that's required in order to achieve that extra support is you have to control which load needs to be on, which load has to be shed, or manage your load shedding. And when do you sync to the grid, when do you require resyncing? And finally, the black start, which is providing electricity after loss of power, or a blackout, basically finding an alternative source whether the local power is lost and we connect to the grid, or the grid power is lost and we start utilizing the local power. In a microgrid, we've got a lot of entities doing the management, and we've got all of these devices interacting. Okay, so distribution management system in a microgrid is a very general concept. 30 years ago, we didn't have any distribution management systems. As we increase renewables and power is not always available, undesirable voltage profile require efficient DMS and EMS systems. That means that we have to complement the microgrid controller with the monitoring system, communication system, and all the compatible primary control. What we also mean by that is a new microgrid would utilize the open protocols instead of the old closed protocols. Okay, so to summarize this section, to control the microgrid, we need all the controls. So we start with the microgrid controller, like the DMC 490. And then we would need to add to it the monitoring system, the industrial communication, and the primary controls in order to achieve an efficient setup of the microgrid and a stable setup. Again, to keep in mind that when you implement a microgrid, it's not only the components that we have to worry about, but also what is the goal of the microgrid. Sometimes, depending on your setup, your main goals might switch around or shuffle around, but they will revolve around either reducing the cost, reducing the emissions, and achieving power efficiency. Hopefully at this point you have understanding where does the microgrid fit in the bigger grid, what are the different levels of controls that we have. So we have decided to show you an example of an implemented microgrid project. Okay, so this is an example of a campus application, and there was challenges given at the beginning of the project, and there was a solution proposed and implemented. The challenges that were given was to reduce emission and electricity cost on the campus while maximizing the renewable resources, and provide a seamless transition between grid connection and on-site generation for critical loads during grid failures. These were the critical to quality requirements that were given to the project team, and the shared project team came up with a solution that would actively control the battery energy storage system, or BESS, and other energy storage sources based on different forecasting engines, providing seamless transition in case of a grid failure, simulation tools to evaluate the performance of the control system when faced with different load and electricity price profiles. So the engines had a way of, or the computing engines had a way of getting data from the local utility for the price and the forecasted tariff as the power is consumed, and based on the calculations, which have infinite number of permutations, the number of permutations of load and generation points and whether to connect to the grid or disconnect from the grid was beyond simple calculation. As you can see, there is 5 buildings, there is many points of generation. You've got the diesel generation, you've got the combined heat power plant, and you've got a battery system. And the idea was turn on the battery system when you can consume power that has been stored at a cheaper tariff, right? And turn on the generators when it is required to provide the power, and sectionalize some of the areas that is not very critical when there isn't enough power produced in order to maintain the critical loads. And at the end of the day, efficiency was achieved. Monitoring the system, they provided a status alarm management with remote access for the managing team. The system is very large, and there was many settings, many studies needed to be conducted in order to achieve the most efficient settings in the system. I think what we need to take away from this is that setting up a microgrid is not just setting a single control box, but it's setting the whole system and having a holistic approach toward achieving the critical to quality goals that is given by the adopters of the system. During the example, we have shown you the DMC490, which is a microgrid controller. The microgrid controller can play many roles depending on the requirement of the microgrid implementation. So it provides the normal role that it would play in the bigger grid, which includes the SCADA and PLC logic. You might need to watch the communication, so that you would need a watchdog application that would monitor the communication, monitor the loss of certain industrial communication setups. And of course, the job is to do all the computing power that's required per the settings that's provided in order to achieve the most efficient cost, kilowatt utilization, and minimization of emissions. Saying that the GE solution includes all the different facets and all the different devices required for implementing an efficient microgrid system, which includes the monitoring, the communication, the controllers, and the basic HVMV requirements. So microgrid was initially viewed as a standalone entity. Now microgrid is viewed as support to the utilities in a plug-and-play functionality. Microgrid is the path to smart grid, and environmental support is the key for microgrid. The microgrid solution, as you've seen, involve many products to make up the microgrid control system. The current key goal of microgrid control system is to optimize generation, cost, load, and minimize the emissions.